Imagine you're standing on this single lane dirt road. A car goes by. Then, after that car completely vanishes over the horizon, another car goes by.
Right. Well, very scenic.
Yeah, exactly. Scenic and incredibly safe. I mean, no one is ever going to crash. But if your goal is trying to move like 1,000 cars from point A to point B, you're going to be standing on that dirt road for a very, very long time.
You'd be there for days.
Right. And that exact bottleneck is really what we're tackling today on this deep dive. We are exploring this, this uniquely narrative technical article. It's called The Secret Life of Python, an Introduction to Concurrency.
Written by Aaron Roth, yeah. Over at tech-reader.blog.
Exactly. And our mission today is to completely demystify how computers juggle multiple tasks at once, basically taking you from that slow, single-lane dirt road to a multi-lane productivity superhighway. Without crashing, hopefully.
Which is an excellent piece to dive into, really, because every system, eventually it has to make that transition off the dirt road. Whether you are dealing with a computer program, parsing data, or even a massive human organization trying to scale up, you inevitably hit this wall where doing things sequentially, strictly one at a time, it just isn't physically viable anymore.
It just doesn't work. And what makes Rose's source material so engaging is, well, it's how he frames this deeply technical subject. He completely avoids that trap of just, giving us dry code snippets on a blank page.
Oh, absolutely. That can be so dense to read.
Totally. Instead, he sets up this wonderfully atmospheric narrative device. He drops us right inside this grand Victorian library in London. I mean, you can practically smell the old paper and the polished mahogany.
The setting does a ton of heavy lifting for the reader here.
Yeah, it does. In this library, code quality is the unspoken objective, right?
Yeah.
Craftsmanship is the only thing that matters.
And it perfectly contrasts the quiet, deliberate, almost slow nature of an old library with the absolute chaotic, microscopic speed of modern computing. Grounding highly abstract programming concepts in a physical space like that, it just makes them so much easier to grasp.
It really does. So navigating this library, we meet our two main characters. First, we have Margaret, who's this wise, seasoned senior engineer. Right? She has clearly seen it all.
The mentor figure.
Right. And then we have Timothy, her eager junior colleague. And right now, Timothy's experiencing a very specific, a very relatable kind of panic.
We've all been there.
Oh, absolutely. Okay, let's unpack this. Timothy has built a brand new application. He calls it Match Logger. And it is designed to record the moves of a chess game for the library's growing chess club.
Sounds simple enough.
Right. And for a single game, it works flawlessly. It logs move after move, totally perfectly. But the chess club has expanded. Today, they have two grandmasters playing two completely different matches at the exact same time.
Ah, the classic scaling problem.
Exactly. Timothy figures, hey, no problem, I'll just have the script start match A, then start match B, and they can both run together. But when he hits, execute absolute disaster strikes.
That just freezes up.
Worse, match B flat out refuses to start until match A is completely 100% finished.
Oh, wow.
Yeah, so you have these two intense grandmasters sitting at the second board, arms crossed, impatiently tapping their watches, just waiting for a computer program to give them permission to start playing.
What's fascinating here is how this delightfully specific, almost comical scene perfectly illustrates a fundamental limitation of standard computing logic.
Yeah, it's such a great visual.
It really is. It sets up the central conflict of the entire architecture Timothy is trying to build. He has just collided headfirst with the default way that computers actually think.
Right.
By default, a computer is like a person who rigidly refuses to start a new sentence until they have completely finished writing the previous one, down to the final period. It is a strictly linear, sequential process.
Which brings us to Margaret, the senior engineer. She steps in to save Timothy from his total embarrassment in front of these grandmasters. She walks over to a whiteboard in the library, and she just draws a single straight line.
A great teaching moment.
Yeah. She explains to Timothy that everything he has written so far is what engineers call synchronous code. Synchronous execution. The one-at-a-time world.
Exactly. One task starts, it fully finishes, and only then does the next task begin.
Right, and this explains exactly why the second chess match couldn't start, doesn't it?
Yep. Under the hood, the CPU was looking at the first match and operating under strict synchronous rules. It's saying, I'm assigned to this game until a king is toppled and someone wins or loses. I'm not looking at anything else.
Even if nothing is happening.
Exactly. It literally doesn't matter if there are 20-minute pauses between moves where the computer is doing absolutely nothing. It is rigidly committed to that single straight line on the whiteboard.
It's so stubborn. Timothy actually comes up with a really solid analogy in the text to describe his frustration with this. He says, it's like a grocery store with 10 shoppers but only one cashier.
That's the perfect way to visualize it.
Right. You have all these people ready to pay and leave, but everyone is just stuck waiting in this single miserable line. But this is where I want to push back a little bit on our source material.
Go for it.
Because Margaret, the seasoned expert in the story, she describes this synchronous single cashier setup as inherently safe. And I'm reading this thinking, wait a minute, if we just want our programs to work reliably, why is being safe suddenly framed as a bad thing?
That's a fair point.
Right. Why wouldn't a software engineer want the safest possible code every single time?
Well, let's clarify what Margaret means by safe in this context, because you're right, it sounds totally counterintuitive. In software engineering, safe usually translates to predictable. It means the logic of the program is incredibly easy to trace, and more importantly, it is easy to debug when something eventually goes wrong.
Because there's a clear order to things.
Exactly. Because execution happens one step at a time, if step 3 fails, with absolute certainty it's because of something that happened in step 2. There is no mystery. You have a completely linear chain of cause and effect.
Right, because there's literally only one thing happening in the entire system.
Precisely. But that safety turns into a massive bottleneck the moment you introduce external factors, what Margaret refers to as the physical world.
Ah, right, the messy physical world.
Yeah. In Timothy's architecture, the physical world is the human chess players. Humans are agonizingly slow compared to processors. They think, they strategize, they get up to grab a coffee.
Right, so the computer's just sitting there waiting.
Exactly. In broader computing terms, waiting on the physical world includes waiting for a large file to save to a spinning hard drive, waiting for a remote database to respond, or waiting for a packet of data to travel across a network.
And while it waits,
Yeah.
it does nothing.
Nothing at all. When your synchronous code hits one of those physical waiting periods, the entire program freezes. The CPU, which is the incredibly powerful brain of the computer, just sits there idling, twiddling its digital thumbs. It completely refuses to do any other work until that specific physical task completes.
So, yes, the code is safe.
Right. But when speed and real-time external resources are involved, that predictability becomes a fatal flaw.
Which means the single cashier is just way too slow to keep up with these tapping grandmasters. The system desperately needs a structural upgrade.
It's time for more lines on the whiteboard.
Exactly. So returning to the whiteboard, Margaret draws a second line, perfectly parallel to the first one. And this introduces our solution, concurrency, the art of managing multiple tasks at once.
A huge leap forward.
Right. We are finally leaving the one-at-a-time world and entering the many-at-once world. But as she draws this, Margaret gives Timothy a very stern warning.
Oh, she definitely does.
She tells him that when you invite more than one worker into your code, you also invite something ominous. She calls it the chaos of many.
The chaos of many. It sounds like the title of an epic fantasy novel, doesn't it?
It really does.
But it is a very real, very stressful reality for systems engineers. The moment you move to concurrency, you intentionally destroy that predictable sequence of events we just talked about.
The safety is gone.
Poof. You are now dealing with multiple sequences of execution happening in overlapping, often entirely unpredictable ways.
Here's where it gets really interesting for me, trying to visualize how this actually functions. Think about it like this. Moving from synchronous code to concurrent code is like moving from cooking a complex meal entirely alone in your kitchen to suddenly having 5 highly caffeinated sous chefs working right alongside you.
Oh, I love this analogy.
Right. If you are alone, it is predictable but slow. They chop the onions, then you boil the water, then you sear the meat, one step at a time. But if you have 5 sous chefs, everyone is working at once.
The meal is definitely going to get done much faster.
Definitely. But, and this is a massive but, you also drastically increase the chances of bumping into each other, violently fighting over the only good cutting board, and accidentally knocking the entire pot of boiling soup onto the floor.
Dropping the soup is a real risk. If we connect this to the bigger picture, your sous chef analogy highlights the fundamental trade-off of concurrency. Margaret actually outlines this explicitly in her cheat sheet at the end of the source text.
Right, the core rule of the concurrency mindset.
Exactly. The rule is this. You should only ever introduce concurrency when the performance gain, the absolute necessity of getting that meal out to the dining room faster, is genuinely worth the extra architectural complexity of managing all those multiple workers.
Because managing them takes serious effort.
A ton of effort. You have to actively coordinate them. You have to write specific logic to ensure they aren't trying to use the exact same resources at the exact same time.
And what happens if you don't manage them properly? Like, what does dropping the soup actually look like inside a computer program's memory?
Well, it's not pretty.
No, it isn't. Margaret warns Timothy about a very specific, very dreaded danger in computer science. It is called the race condition. And the example Aaron Rose uses in the text to illustrate this is just hilarious, but it perfectly captures why this is a complete disaster.
The daily summary file, right.
Yes. Imagine the chess club has a single text file on the hard drive called the daily summary file. This is where the final results of the matches are saved for the historical record.
So this is the digital equivalent of your kitchen's single cutting board.
Exactly.
It is a shared resource that both concurrent workers need to access to do their jobs.
Right. So imagine both chess matches conclude at roughly the exact same time. Both concurrent workers race to the daily summary file to write down the winner at the exact same millisecond.
This is where the chaos starts.
It really is.
Yeah.
Match A's worker grabs the file and starts writing winner, Timothy, but only gets halfway through. It writes TIM. At that precise microsecond, Match B's worker violently interrupts, shoves Match A aside, and starts writing its own result. Winner, Margaret.
Oh.
Then Match A pushes back, regains control, and finishes its word. The file gets saved, and when you open it up, the official permanent record of the chess club says, winner, to Margarethe.
Tim Margarethe. It is a ridiculous word to say out loud, but it represents a catastrophic failure of data integrity.
Right, because it's nonsense.
Yeah. I mean, in a banking application, that's not scrambled letters, that's scrambled account balances.
It is a total mess. I was laughing reading this, but Margaret explains it brilliantly with a simple pen and paper analogy.
She's good at those.
She is. She tells Timothy, in a single-threaded world, the synchronous world, you are the only one with a pen. You could write at your own pace. Now, everyone has a pen, and they're all fighting for the exact same piece of paper.
It's a great visual.
But here's what I want to clarify about the mechanics of this. So when the operating system context switches between these threads, it's completely blind to the fact that the word Timothy is a single logical data payload, right? It just slices the execution up at the microsecond level.
This raises an important question, and you've hit on exactly what makes concurrency so notoriously difficult to debug.
Because the computer doesn't know what it's breaking up.
Exactly. The operating system is the ultimate manager of these workers, and you're right, it is completely blind to context. It doesn't know what a word is or what a completed thought is. It only sees a stream of binary instructions.
Right. Just raw data.
Yeah. To give the user the illusion that multiple things are happening simultaneously, the OS rapidly slices up CPU time. It might let worker A execute 3 instructions, then mercilessly pause worker A, saving its current state to memory, and let worker B execute 4 instructions.
So it's just abruptly cutting them off mid-action without any warning or regard for what they were in the middle of doing.
Exactly. A race condition is a bug where the core logic of your program unpredictably depends on the exact microscopic timing of how the operating system decides to slice up and switch between those workers.
It's basically a lottery.
It really is. Who reaches the finish line first? Who gets paused the absolute worst possible millisecond? You don't know. The developer doesn't know.
Wow.
And critically, it changes every single time you run the program. It is completely non-deterministic. One day the summary file says Timothy, the next day it says Margaret, and the third day it says Tim Margarethe.
That sounds absolutely terrifying if you are trying to build something reliable.
It is the stuff of nightmares for developers.
I bet. But we know we have to do it. We have to give the chess club 2 cashiers because the grandmasters are still tapping their watches. So before we even pick which concurrency model to use, how do we fundamentally prevent the Tim Margarethe disaster? How do we stop the workers from trampling each other?
This is where we introduce the concept of locks. If a race condition is the chaos, a lock is the strict rule of engagement.
Okay, locks.
Yeah. Margaret explains that before a worker is allowed to write to that shared daily summary file, it must first acquire the lock for that file.
Okay, to use another analogy, it's exactly like a physical key to a single occupancy gas station bathroom.
Oh, I like that.
Right. You cannot enter the shared space unless you are physically holding the token.
Whoa.
If worker A has the key and worker B shows up, worker B just has to stand outside and wait.
That is a perfect visualization. And mechanically, what happens is the operating system respects that lock.
Oh, it does.
Yes. If thread B tries to access a locked resource, the OS actively suspends thread B. It won't give it any more CPU time until thread A finishes its work, saves the file, and officially releases the lock.
So it hands over the bathroom key.
Exactly. The key is handed over, and only then can thread B proceed. It forces a small, controlled moment of synchrony one-at-a-time execution just for that specific shared resource, keeping the data totally safe.
Okay, so we have the bathroom key. We know how to protect the data. Now we have to actually build the multiple cacheers. Margaret outlines 3 distinct paths, 3 different tools in Python to achieve concurrency.
Right, the implementation phase.
And choosing the right one isn't just a matter of preference, is it? It's about identifying the specific type of bottleneck your system is facing.
Precisely. You have to know your enemy.
Exactly. So the first tool she brings up is called threading.
Yes, threading. This is specifically designed for situations where your bottleneck is waiting on the outside world, what we previously called I/O, or input-output operations.
Right, the slow physical world.
Right. If your program spends 90% of its time waiting for a massive file to download, or waiting for a network request to clear, or waiting for a slow database to return a query, threading is your go-to tool.
And mechanically, how does threading actually achieve this under the hood? Like, how does it handle the weight?
So with threading, the operating system spawns multiple threads of execution that all live inside the exact same memory space. They are all sharing the same kitchen, to use your earlier analogy.
Okay, shared kitchen.
But the magic happens during the wait times. When thread A sends a request to a database, it knows it has to wait for a response, so it voluntarily yields control.
Oh, it just steps back.
Exactly. It steps back, and the OS instantly switches focus to thread B, letting it do its work. By the time thread B needs to wait for something, thread A's database response has arrived, and the OS switches back.
So they aren't technically working at the exact same microsecond.
Right. They're still taking turns on the CPU, but they are hiding the wait times by overlapping them.
Okay, so that perfectly solves bottlenecks caused by waiting.
Yeah.
But what if we aren't waiting? What if our bottleneck is just pure, heavy calculation? That brings us to tool number 2. Multiprocessing.
Multiprocessing solves a fundamentally different problem. You use this when you are CPU bound.
CPU bound, meaning the brain is doing all the work.
Exactly. Imagine you need to process a massive data set from machine learning, or encode a 4K video, or calculate complex physics models. These tasks don't wait, they completely consume the CPU.
So threading wouldn't work here.
Not at all. If you tried to use threading for this, the threads would just viciously fight over the CPU, constantly interrupting each other, and the overall process would actually take longer because of the overhead of switching back and forth.
So how does multiprocessing bypass that fight?
It bypasses it by completely separating the workers. Instead of spawning threads inside one program, the operating system literally forks the program.
Wow, it clones it.
It creates entirely separate, independent instances of your application. Each has its own dedicated memory space, its own variables, and its own direct pipeline to a different core of your CPU.
So going back to the sous chef analogy, it is like building a completely separate kitchen next door. You sous chefs never even see each other.
That's exactly it. They are in their own isolated worlds. But the catch is, because they are in different kitchens, passing data between them requires serialization, packaging up the data, and sending it over, which introduces its own heavy performance overhead.
Right, which sounds incredibly powerful for number crunching, but very resource heavy to set up.
Very much so.
And then we have the third tool, which sounds designed for modern web architecture, Asyncio.
Asyncio is fascinating because it is designed entirely for massive scale.
Okay.
If threading is great for managing a dozen simultaneous tasks, Asyncio is engineered for juggling thousands or even tens of thousands of them.
That's a huge jump.
It really is. It is heavily used when you have a massive number of lightweight, simultaneous network connections. Think of a real-time chat application like Discord or Slack, with 20,000 users connected to a single server at once.
Right, because you can't just spin up 20,000 separate threads, right?
Yeah.
The operating system would collapse just trying to manage the context switching.
Exactly. The overhead of the OS switching between 20,000 threads would consume all the server's memory and CPU before it even processed a single message.
So how does Asyncio handle it?
Asyncio solves this by abandoning the OS manager entirely.
Wait, really?
Yeah. Instead, it uses a single thread and something called an event loop. It is cooperative multitasking. The application itself juggles the tasks.
Okay, so the app is in control.
Right. When one connection pauses to wait for data, The code explicitly tells the event loop, I'm waiting now, go help someone else.
Oh, that's clever.
It is like having one incredibly efficient waiter managing 50 tables, rapidly bouncing between them the exact microsecond someone closes their menu, rather than hiring 50 individual waiters to stand motionless at each table.
That's a great way to put it.
It is highly efficient, but it requires writing your code in a very specific, specialized way.
So what does this all mean for our protagonists back in the library? We have threading for I/O waits, multiprocessing for heavy CPU calculation, and Asyncio for massive network scaling. Looking at these three options, why does Margaret specifically decide that threading is the perfect tool for Timothy's chess club dilemma? Why not build the second kitchen with multiprocessing?
Well, because Margaret is applying the concurrency mindset perfectly. She is looking closely at the specific nature of Timothy's bottleneck.
Right, the grandmasters.
Exactly. What is MatchLogger actually doing mechanically? It is not calculating complex physics for the next chess move. It is not handling 10,000 chat users. Most of the time, MatchLogger is doing absolutely nothing.
It's just sitting there.
It is waiting. It is waiting for a human grandmaster to stare at the board, scratch their chin for 5 minutes, pick up a knight, and move it.
Which takes forever in computer time.
Right. That is a textbook I/O operation waiting on external inputs and the physical flow of time. Because the program is heavily I/O bound, threading is the perfect lightweight fit.
That makes total sense.
It allows one thread to sleep peacefully while waiting for board A, while the second thread instantly wakes up to record a move on board B.
It really is all about picking the right tool for the job. You don't need a sledgehammer to drive in a thumbtack.
Exactly.
So Margaret tells Timothy they're going to use threading. They're going to give the chess club those 2 cashiers. But she adds that crucial final step. First, they have to implement those locks.
Yes, the locks.
They have to pass around that bathroom key for the daily summary file, so only one thread can hold a pen at a time, completely preventing our friend Tim Margaretti from ever making an appearance.
Precisely. You introduce the workers to get the required speed, and then you must introduce the strict coordination rules to tame the resulting chaos.
This has been such an illuminating journey through Margaret's concurrency mindset. If you're tracking with us so far, the core takeaways from Aaron Rose's excellent article really boil down to understanding your bottlenecks.
That's the heart of it.
Synchronous code is the one-at-a-time, world easy to debug, but painfully slow if you're waiting on the physical world. Concurrent code is the many-at-once, world-fast and efficient, but it invites the chaos of many.
And you have to watch out for race conditions.
Right, where multiple tasks try to change the same piece of data at the same time, leading to corrupted information. And ultimately, you only introduce this complex architecture when the need for speed absolutely demands it.
It is a constant, delicate balancing act between maintaining simplicity and achieving actual performance.
And here is why this matters. Even if you never intend to write a single line of Python code in your entire life, this inherent trade-off between speed and complexity, it applies directly to how we manage human teams, human workflows, and entire businesses.
Oh, absolutely. It scales up perfectly.
Right. Think about your own work environment. How often does management assume that throwing more people at a delayed project will automatically make it finish faster?
It is one of the most common organizational fallacies. The blind assumption that 10 cashiers are always mathematically 10 times faster than 1.
Exactly. But if you just throw more people at a project, adding more cashiers and more sous chefs, without incredibly careful coordination and locks in place, you don't get speed, you just get human race conditions.
That is so true.
You get 2 project managers accidentally overwriting the same shared tracking spreadsheet. You get duplicated effort because 2 teams didn't realize they were building the exact same feature.
Stepping on each other's toes constantly.
Constantly. And you end up spending more time in endless coordination meetings than you do actually producing meaningful work. The logic of computer science maps perfectly onto the logic of human collaboration.
The chaos of many doesn't care if the workers are silicon microprocessors or human beings sitting in cubicles. Shared resources always require strict rules of engagement, otherwise the integrity of the work completely collapses.
It really does. And as we wrap up this deep dive, I want to leave you with a final thought to mull over, something that builds on everything we've explored today regarding scale.
Let's hear it.
We've seen how even 2 concurrent tasks, just 2 simple chess matches, can lead to bizarre, non-deterministic chaos like Tim Margaretti if they aren't perfectly managed with flawless rules.
Right.
Now think about the bleeding edge of technology today. Think about modern artificial intelligence systems. Think about the massive neural networks that generate human language or create photorealistic images.
Okay, I see where you're going with this.
These systems process millions of concurrent tasks simultaneously across thousands of processors. They are the ultimate, unimaginable expression of the many-at-once world.
The sheer scale of concurrency required to train and run modern AI is almost incomprehensible compared to a simple logging script.
Right. So the provocative question is this. If concurrency teaches us that giving multiple workers a pen inevitably leads to chaos without flawless, mathematically perfect rules, well, how might these unimaginably complex AI systems be silently suffering from their own invisible race conditions?
Wow, that is a heavy thought.
When an AI spits out a bizarre, nonsensical answer, are there microscopic, non-deterministic collisions happening deep inside the black box that we haven't even discovered yet? Bugs and corrupted thoughts that are so complex, spanning across millions of parallel threads, that we don't even have the diagnostic tools to recognize them as execution errors.
It truly makes you wonder how much of what we currently label as AI hallucinations might actually just be the ultimate million-lane highway pileup of concurrent logic.
It really does. So the next time you find yourself stuck waiting in a long line at the grocery store, staring at that single, slow cashier, take a deep breath.
Enjoy the peace and quiet.
Yeah, exactly.
Yeah.
Appreciate the predictable, methodical safety of the one-at-a-time world. Because as we've learned today, paving that single-lane dirt road into a multi-lane superhighway is entirely possible. But if you don't carefully coordinate the traffic, you might just end up wishing you were back on the dirt road. Thanks for joining us on this deep dive. We will catch you next time.